welcome to this talk, and I'm glad to see UKZN for physically and also people who are connecting electronically. So this is we used to have seminars in the past under the banner of NITheCS, but now there's a new organization in town, NITheCS, the National Institute of Electrical and Computational Sciences, which will officially kick off on the 1st of April. Right? Yes, I think that's the official date. And so this is the first really. Francesco felt that we should have these talks about the 5 nodes, and this is the first one that's taking place, I think, at this node. And it'll take the form of a webinar, and we'll try to maintain that as we go. Focus on the physical presence and then also the online presence with those who are outside the Western campus. So we hope that this seminar series will become a regular thing. And I think it will help to bring us all together. And now, NITheCS covers all of the basic sciences. Previously, it was physics, electrical physics. And we will attempt to get speakers, and please nominate visitors, how many people that you know, for future seminars. And I think the objective is to generate eventually interdisciplinary research as much as possible. So thank you, Ian, for helping with logistics, and Nelly. Nelly's right. And Celine Fatima. Intelligence organization. Nelly had indicated that there will be some tea, coffee, and snacks afterwards, so please don't rush off. We will be outside and give us a chance to network. So, Celine reminded me I should say something about the International Year of Mathematics, which is today, but I won't go any further than that because I noticed that our speaker, Ritu, has got some slides dedicated to that, so he can say something about that. So our speaker today, I think most of us know, is Professor Ritu and Goswami. He is a member of staff now for about 12 years, or in the School of Math Science, Computer Science, and he's a professor. He's a professor of applied mathematics, and he's also academic leader of research. And he seems to like administrative work because he's taken on the new directorship of ARC, the Physics Research Center, and he also holds leadership positions within the COE MAS, the Center of Excellence in Mathematical Sciences, the UCDP, University Capacity Development Program, there's NGA, the National Graduate Academy. But these are positions which effectively help in developing new talent in mathematics and support for young postdocs and stuff. So he has many, his research is in gravity, but he has many wide interests. He publishes in a variety of fields, and this is reflected in the talk that he's going to be giving today, which is in another day. So this is the sort of thing that we're trying to inculcate and generate. So with that, I'll ask Ritu to take over.
Thanks a lot, Dr. Maharaj, and it's a great honor and pleasure for me to start the NITheCS colloquia series in UKZN. It's really good. And whoever has listened to me before, for you it's a pleasant change because I won't be talking about black holes, naked singularities, space-time manifolds, and topology, etc. Absolutely brand new topic, number 3. Right. So as Sunil pointed out, today is the International Day for Mathematics. The reason being, if you write today's date in the American way, month first, date later, then it's 3/14, the first 3 digits of pi. So that's why it's also called a pi day. But anyway, I'm not very much fan of American way of writing dates. And secondly, I don't think, 14th of March is a very good day for people who are afraid of mathematics, because just tomorrow is the famous or infamous Ides of March. Beware of Ides of March or Caesar, if you remember. That was what the soothsayer said. And Caesar got assassinated on Ides of March. Anyway, since it's an International Day of Mathematics, I thought the best way to start would be to talk about these two gentlemen of two different eras who were, I would say, who had superhuman capabilities in mathematics. They were superheroes of mathematics. So you can as well call them math man, possible. So today's topic is such, the partition function, on which both of these math men had wonderful contributions. Now, talking about partition, you see, it depends on what context you are using partition. There can be a lot of meaning. For example, if you are using partition in political and socio-economic context, partition of countries, it comes with war, bloodshed, famine, everything, all packed together. And it's a covariant thing, be it Palestine, be it Sudan, be it Ethiopia, be it India, it's always the same. Fortunately for mathematics, the word partition is not that bloody, but it posed a lot of difficult problems which lingered for centuries. So let me define what do I mean by integer partition. So in number theory and combinatorics, partition of a non-negative integer n is also called an integer partition, is a way of writing n as a sum of positive integers. So let's give you an example. Say, take the positive integer 3. You can write it as 3, you can write it as 2 plus 1, you can write it as 1 plus 1 plus 1. Similarly, for 4, you can write it as 3 plus 1, 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. Oh, sorry. Yeah, that's a typo. Sorry. Here. So now the question is, how many partitions a positive integer n will have? Now, if somebody asks me this question, my first question would be, will you let me have permutations? Because interestingly, if permutation is allowed, this question is quite simple. A high school student can do it. In fact, I was thinking of giving it in one of the Olympiad problems. So how to do it? Suppose I want the partition of n with permutation allowed. So I write n once with blanks in between. Now each blank has two options. Either you throw away the blank and bring that 2 ones together to make a 2, not 11, 2, or put a plus sign in the blank. So just by these two options, you can generate all the possible partitions and permutations of partitions using this. And then it's very easy to count, because how many blanks are there between n ones? Of course, n minus 1. Each blank has two options. So what is the total number of options? 2 to the power n minus 1. Perfect. So what's big hullabaloo about this? The problem is that in this count, we counted 1 plus 1 plus 2, 1 plus 2 plus 1, 2 plus 1 plus 1 as 3 separate partitions. You can see they are not separate, right? We are just permuting the same partitions. So counting becomes extremely difficult when permutations are not allowed. And this is a difficult problem, and as all the difficult problems during that time did, they landed up in this mathman's desk. And to start with, what he did was perhaps the same thing as what I do. Bring all your postgrad students and postdocs, give them a pen and paper. Yes, write down the partitions of first 30 natural numbers and bring it to me. So most probably he did that and got something like this. Oh, by the way, let me tell you, the first one, the partition, was of 0. Now we all know 0 is a very powerful number, but very problematic. And by the definition of our partition, we know that 0 is not a positive integer. So we should not bother about it. But just for completeness sake, perhaps Euler said, okay, let's count the partition of 0. But how will you count the partition of 0 anyway? 0 is not a sum of two positive integers, no. But at least you can write 0 as 0. And perhaps Euler was a good person like me. If a student writes something, I give 1, not 0. So yeah, so he said, okay, let's take the partition of 0 to be 1. So by looking at this, now he was trying to see a pattern, if he can find a pattern in this series, which is the infinite series, of course, goes on. Now, if you see the first few numbers, 1, 1, 2, 3, 5, this pattern corresponds to a pattern which was very famous, and perhaps we all know, the pattern of Fibonacci series. So what is Fibonacci series? You take first two ones, and then the next number is the sum of the previous two numbers. So it will be 1, 1, then 2, then 3, then 5, then 8, and goes on. So the first part looks absolutely similar to the Fibonacci series. So let's do something like this. So let's write it, and we are trying to find some pattern. So you see 1 plus 1 equals 2. Nice, the Fibonacci series work. 1 plus 2 equals 3, it works. 2 plus 3 equals 5, works. But then we have a problem. 5 plus 3 is 8, but our next number is 7. So what Euler thought was that, sort of, perhaps you can see what we are doing. So this is the number series, and we are inserting a slide rule from the left. Beyond that one, everything is 0. So whatever plus or minus in the slide rule is, that doesn't matter. We are inserting it and to generate the next number. So after here, we see that there is a problem. So playing on the same spirit, why don't we put a minus there? In other words, we are adding the first previous and the second previous number and subtracting the fifth previous number. Does it work? Okay, it works for 7. For 11, 7 plus 5, 12, minus 1, 11, perfect. But then again, we have a problem. 11 plus 7, 18, minus 2, 16, but this is 15. So we need to put another minus. Okay, just tweaking, trying to find patterns. Fine. Right. So now what? We have 2 pluses and 2 minuses. Does it work? 15 plus 11, 26, minus 3, 23, minus 1, 22. Perfect. 22 plus 15, 47, minus 5, 42, 37, minus 5, 32, minus 2, 30. Works. 52 minus 10, 42. Brilliant. We have hit a jackpot. 72 minus 16. Sorry, yeah. 72 minus 16, 56. It absolutely works. Again, we are facing a problem. 56 plus 42 is 98. Minus 22 is 76. We have 77. So playing like this, we need to put another plus. So you remember how we started with? We started tweaking the Fibonacci sequence. So what Euler found in this way was that this tweaking will go on infinitely. At no point this tweaking of Fibonacci will stop. So that means there is the infinite slide rule from the left, which we have to put in with pluses and minuses. One more thing he noticed, that this plus and minus always comes in pairs. So there will be always 2 plus, then 2 minus, 2 plus, 2 minus, like that. Well, to tackle one infinite sequence with another doesn't help at all. So what he tried to see was at which positions this plus and minuses come. So he thought, let's write down the position sequence, which is again an infinite sequence. Now the position is of course backwards, but we write it in the forward fashion like this, that if we want to find the partition of a given number, we add the partition of previous number and the second previous number, then subtract the partition of fifth previous number and seventh previous number, then add the partition of 12 previous number, 15 previous number, and goes on till infinity. Well, now you can see a very nice pattern in this sequence, right? No? Even I can't see that. Anything. So as a poor man, what I do is whenever I don't see pattern in a sequence, that's all I learned in my high school, the first thing is try to find the difference between two numbers of the sequence. And if we see if we can find a pattern. So this was our position sequence. And this is the difference between two numbers in the position. So 2 minus 1 is 1, 5 minus 2 is 3, so on and so forth. Is there a pattern here? Well, apparently it's hard to see, but if I put some color in your life, it may be easy to see. Now, if somebody cannot see a pattern in the yellow numbers and you are in this room, you really need help. And so is the blue numbers. You can immediately see a pattern. So finally, we got a pattern in the difference of position sequence. So with this pattern, we can generate the position sequence. And with the position sequence, putting the pluses and minuses in pairs, we can actually algorithmically find the next partition in the original partitions. But hang on. Just now I said Euler was a math man. Did he solve this in a dumb way like I did now? No. As soon as he saw the position sequence, he found a pattern. How? Now for that, we need to go back to a history a few thousand years back, rather a couple of thousand years back. From Pythagoras' time, people were studying geometrical numbers. For example, the first type of geometrical numbers are triangular numbers. So what are triangular numbers? The nth triangular number is that number if you can arrange objects of that number into a nice equilateral triangle upside down. So you can see this is the first triangular number, second triangular number, third triangular number, and so on and so forth. Now, how to find the formula for triangular number? It's very clear. It's the sum of first n natural numbers. So it is n times n plus 1 by 2. Everybody knows that. What comes next after triangle? Square. I don't have to explain what the square numbers are. So simple n square. Now, if you give a child a square and a triangle, what the child would do? Put a triangle on the square and make a house, right? That's how children draw houses. A square and a triangle. And how many sides that house has? 5 sides. Don't double count the top layer of the square because you are putting the nth square on nth triangle on nth square. And press it a little bit, you get a nice pentagon. And since you are not double counting, it will be n times n minus 1 by 2. You sum it up. So these are pentagonal numbers. Now, when Euler saw the position sequence, he immediately saw the blue numbers are pentagonal numbers. You put n equals 1, you will get 1. You put n equals 2, you'll get 5. You put n equals 3, you'll get 12, and so on and so forth. Okay, so blue numbers are taken care of. What about the yellow numbers? Now, here comes the example why I say Euler was a superhero. You know, most of his life, he was nearly blind to blind. But perhaps he could see more than anybody else, anybody and everybody else. So turns out these yellow numbers are also pentagonal numbers with negative value. Put n equals minus 1, you will get 2. Put n equals minus 2, you will get 7. So immediately he saw the position sequence, he knew what is the sequence and how to algorithmically generate the partition numbers. You see how number theory, geometry, they are all so beautifully related. It's crazy. So this was the situation of partition function or the partition numbers in the 18th century. Then what our next madman did. So it turns out when he visited Cambridge as a guest of Hardy, he got interested and started playing with this partition function. Now, Ramanujan playing with something is a very, very serious issue, believe me. So just by playing with it, he came up with some brilliant results. That partition of any number which is a form 5k plus 4, that means any number which ends in 4 or 9 must be divisible by 5. Out of nowhere. So that means you see, P4 is 5, P9 is 30, P14 is 135, P19 is 490, they are all divisible by 5. This is not a if and only if relation, by the way. You can see some other numbers are also divisible by 5, so that's fine. But any number which ends in 4 or 9 must be divisible. Similarly, this one. Any number of the form 7k plus 5 is divisible by 7. Take k equals 0, p of 5 is 7, take k equals 1, p of 19 is 4, p of 12 is 77, k equals 2, p of 19 is 490, so on and so on. Again, this is another crazy result. Any number of the form 11k plus 6 is divisible by 11. Here they are. Now, till now, we knew algorithmically how to generate the sequence of partition numbers of any partition. But you see, this is in 1910s and 1920s. People didn't have computers. So now the obvious question was that does there exist a closed form formula for Pn, just like we have one for the Fibonacci sequence? So this was a well-known formula for nth Fibonacci number. And by the way, this is another very, I would say, fantastic formula in number theory. You see, this is phi, the golden ratio. And phi is said to be the most irrational number. Why? Because you cannot cut off phi. When you write phi in a continued fraction sequence, it's 1 plus 1 by 1 plus 1 by 1 plus 1 by 1. So anywhere you cut off, it's nowhere near a rational approximation. So that's why phi is called the most irrational number. So you are raising to the power n the most irrational number, etc. And this is 1 by phi. And you are dividing by root phi. Not only you get a rational number, you get an integer. All irrationality just goes away. So so the question was, can we have a closed form formula for Pn? Well, Ramanujan being Ramanujan, he had some idea, of course, took it to Hardy, they polished it up a little bit, and came up with this monster. Look at this formula. I mean, clearly, by the way, this V is how much accuracy you want. If you want maximum accuracy, you take it to infinity. So when I sometimes look at this formula, you see it has all the module codes for maths major. You see it has maths 130, infinite summation 140. It has trigonometry, it has exponential, it has pi, it has I. What else do you need? So in principle, anybody who is doing a maths major and finishing the third year should understand this formula. I said should, I don't say they do understand anyway. And this function is called Dedekind's function, this SMK. So anyway, of course, it's very hard to work with this. So Ramanujan could immediately see if we allow sufficiently large n, I'll come what does sufficiently mean, that formula, all the other terms drops away and you have a very nice exponential kind of a thing with a 1 by n. Now, this form is an approximation of an approximation. Remember, the previous one was an approximation. So this is an approximation of an approximation. So you don't expect it to work very nicely, right? Let's see how does it work. Till 20, blue is Ramanujan, red is the original. Okay, you can see they're going apart a bit. That's what you expect from an approximation to an approximate of an approximate, right? Let's increase n. Oops. They are like joint twins. And you increase n more and more. And how much I have increased n to? Only 8. So you see, that's what Ramanujan was. His approximation of an approximation looks as good as this. Right, so this is, in a nutshell, the whole history of partition numbers and partition functions. Of course, this hasn't come to an end. A lot of small and different problems people are working on in this. And it turned out quite accidentally. I started working with on this with my esteemed colleague who is sitting here, Professor Prof. Now, people who doesn't know Professor Prof. Pillai, he is the grand old man of mountain of South African mathematics, South African mathematics education, South African Maths Olympiad, to name anything. So he sits there. So it was quite fortunate for me that we started working together on this. So what we are looking for here? So what we are looking for is this. In how many ways can a given positive integer s be written as a sum of terms of arithmetic sequence of positive? In other words, we are trying to look at the subset of partitions which can be casted into an arithmetic sequence. And everybody knows what is an arithmetic sequence. It starts with the first number a, and every other number you add a common difference d, like this. So let me give you a simple example. Say the number 25. I can write 25 as 5 plus 5 plus 5 plus 5 plus 5. This is an arithmetic sequence, by the way, with the common difference 0. So it's called a constant arithmetic sequence. Or I can write 25 as 3 plus 4 plus 5 plus 6 plus 7. This is the arithmetic sequence with a common difference 1. Or 1 plus 3 plus 5 plus 7 plus 9. Another arithmetic sequence with a common difference 2. So this was our question. Given any number n, I don't know what's the number, in how many ways we can decompose or find the partitions of those numbers which are arithmetic sequences. Right. So what are the key points in our quest? By definition, an arithmetic sequence has at least 2 terms. You are talking about a sequence, right? If it's only one term, it's not a sequence. If it's only one movie, it cannot be a sequence, right? You must have at least 2 movies. In the other way around, all 2 sequences are arithmetic. They are not, interesting enough, but they are arithmetic. So to calculate the number of sequences, we'll calculate all the 2 sequences. Also, an important point is arithmetic sequence written backwards is also an arithmetic sequence, but now with a common difference minus. Again, for completion, whenever we find an arithmetic sequence with non-constant arithmetic sequence, we'll just double count it to take care of this. So what is our goal? To find all integer set A, which must, the first term, which must be greater than 0 or greater than or equal to 1. The number of terms n, which must be greater than 1, at least 2, and D, such that the sequence sums up to a given number S. So we all know that sum of an arithmetic sequence is given like this. Now, just by looking at it and knowing that we are just dealing with integers here, no fractions, we can immediately see that n must divide 2s. That means n must be a factor of 2s. And since this term 2a is an even number, 2s by n and n minus 1d must have the same parity. They must either be both odd or both even. Also, since a must be greater than 0, which implies this, that means the number of terms must lie between these two numbers, whereby this thingy, I mean, it's the floor of this number, because you can see it may not be an integer, where alpha d goes like this. Right. So we can just put all of them nicely into a theorem, which says that if S is a sum of an arithmetic sequence, then n is a factor of 2s, as I said, and n must lie between this range. 2 must be less than n less than the floor of alpha d, where alpha d is given like this, and 2s by n and n minus d must have the same parity, and in that case, a is written like this. And the converse is also true, that if n and a satisfies 1 and 2, then a is a natural number and s can be written like this. Perfect. So now we have an algorithm to count what are these sequences. So let's take a set G, which is a set of all integers which are a factor of 2s, intersection this set 2 and alpha d, and these two have the same parity. Now we have a counting function that CD is fs minus 1 if d is 0. Oh, by the way, if, for constant sequences, we can immediately see that it must be the factors of number of factors of s minus 1, otherwise gds, otherwise. And then we define a function curly n from natural number to natural number, which gives us number of all possible arithmetic sequence that sums up to a given number s greater than 2. And then this function is given in this following way. We are summing over all d's. We know it's from 1 to s minus 2. So can we get a total count formula? Yeah, it is a bit complicated, but I'll explain. So it's the formula goes like this. So let s be a natural number, and let's define the following. This bar fs is the number of factors of s. As is the set of all factors of n of 2s in the interval 3 to this. By the way, I have taken the two sequences out because it's any two sequences very easy to count. A0s is the set of all factors of As, and AES is the set of all even factors in As. And n is given this 2s minus n times n minus 1 floor of this. ES is 2 if s is odd, and ES is 3 if s is even. It's getting more and more complicated. C1 is the number of even n's for which n is odd and n does not divide s, while C2 is the number of even n's for which n is odd and n divides s. It's quite complicated, all these 6 things, but then brilliantly we can write down ns as a formula. Let's give you an example. Let's work it out together. Say I have s is 105, whose prime factorization is 3 times 5 times 7. So what is the number of factors of s? Of course, 1 is there, factor of everything. Then 3, 5, and 7. Then 15, 21, and 35, and 100. So the factors of 105, total number of factors is 8. This is the odd, so epsilon s is 2. What is this our 1 plus square root 8s plus 1 by 2? 8s is 840. 841 under root 841 is 29. 29 plus 130 divided by 2 is 15. Perfect. What is the factors of 2 times S, that means 210, between 3 and 14, because this is 15, 3, 5, 6, 7, 10, 14. Odds of this is 3, 5, 7. Evens of this is 6, 10, 14. Perfect. Now you write ends, 3, 5, 6, 7, 10, 14. The blues one are even, yellows are odd. Find out ANs. If you remember, AN was this. For all of them, C1 is 1, only 1, C2 is 0. And then you can just add it off everything and find N105 is 270. Okay, not very efficient way, but at least you can, I mean, given any large number, you can count what is the number of NS. The important point is, you see, this number critically and crucially depends on the number of factors. Isn't it fantastic? Because we are trying to find out an arithmetic sequence where we are adding up terms. So it's one, binary operator, addition, but it depends on the other binary operator, multiplication, which is a factor. So from here, it's very clear that then this thing should be very easy for prime numbers, because prime numbers has the least factors. So what happens when S is a prime? So immediately we saw that a prime number P can't be written as a sum of a non-constant arithmetic sequence of positive numbers with greater than 2 terms. So this, naturally, we get another characterization of prime numbers. We cannot write any prime number with an arithmetic sequence, non-constant arithmetic sequence greater than 2 terms. Another important thing is the set of all fixed points that are greater than 4 of this function ns is exactly same as all the primes greater than 4. What I mean is, take any prime greater than 4, let's say 5, then n of 5 is 5. N of 7 is 7. N of 11 is 11. So they are fixed point, n of s is s. So that's exactly what it is. For all s greater than 4, n of s is s, if and only if, by the way, if s is prime. Otherwise, n of s is always greater than s. Now, initially I said I was really honored because I worked with Professor Pillai. But let me tell you, there is a problem working with Professor. Because he's extremely hard work. And on the contrary, I'm extremely lazy. So I still remember he sent me a 10-page thing of finding n of different numbers and told me, please calculate all of them and see if I'm right. And I was thinking, oh no, I have to calculate, I have to check all these 10 pages now. So being as lazy I am, I wrote these 10 lines instead. Let someone else check it. Now, it's not only for checking. What happened was, after I wrote this 10 line and executed, within, say, 5 or 10 seconds, I could generate NS up to 1000. So then it gave me the same effect as I can just look at the numbers and try to see if I can find some pattern. So in this table, I have only given up to 120. So the first column is the number S, the next column is NS, and the third column is NS/S, the floor of that. So just by looking at it, first and foremost, it was very clear that this function NS is neither 1-to-1 nor on-to. Anyway, I was not expecting 1-to-1 or on-to. I was not expecting to find the inverse function, so it's fine. But what other thing that struck me was the number of odd NS is much more than number of even NS. And this cannot be statistical, just check. Just by looking at this table, can you guess when we are getting an even? In fact, most of them are odd, between 1 and 120. Only a handful are evens. Yes. So in fact, there is a very nice if and only if proof that only when S is perfect square, NS is even, otherwise always it is odd. Similarly, n of any prime square, we could prove that it will always be p square plus 5, so on and so forth. Now, last one is very interesting. Of course, we don't have a perfect closed form formula for ns, just like we don't have for Pn. But can we set up a boundary? And it turned out we could. So in the first iteration, in a very rough calculation, I found ns must be in between s and 5s. Then I changed it and I got it should lie in between s and 4s. Then Professor Pillai came to me and said, I think I can make it better. And then we again worked together, and it turned out that ns will always lie between s and 3s. So this is very interesting. We didn't have an exact formula for ns, but we could exactly calculate it out. Okay. Also, one interesting thing we found out, we could relate our work with another important concept which Ramanujan gave in 1915, which was highly composite numbers. Now, what are highly composite numbers? Ramanujan defined it as, I define a highly composite number as a number whose number of divisors exceeds that of all its predecessors. So in a way, intuitively, you can think it as anti-prime number. Prime numbers has no divisors except itself and 1, and this has a lot of divisors. Now, why do we need these numbers? Interestingly, we use these numbers every day. Have we ever wondered why 60 seconds a minute, 60 minutes an hour, 24 hours a day? Why these funny numbers? You see, day, month, and year are fixed by the celestial movements. I agree. But anything below that, I can always rescale my time and say 100 seconds a minute, 100 minutes an hour, 10 hours a day. How many seconds in a day? 10 to the power 5. How many seconds in a year? 36,500,000. So easy to calculate. Why this funny number, 60, 24? Turns out these are all anti-prime numbers or highly composite numbers. And why do we need that? So that we can, in principle, count the fractions of this. 60 minutes an hour means we can actually count half an hour, 1/3 of an hour, 1/4 of an hour, 1/5 of an hour, 1/6 of an hour, 1/10 of an hour, 1/12 of an hour. Which 100 didn't have this? So anti-prime numbers as numbers or highly composite numbers are very interesting. And what we find out was, if a number is highly composite, then our function ns will be greater than all its predecessors. This thing goes through. Also, if we define something like a number s is called a highly arithmetically decomposable, if ns by s is always greater than 2, what we found out was still very large highly composite number of the order of 10 to the power 5, more or less ns by s is always the greater than 2. So this we could not prove, but we conjectured that set of highly composite numbers greater than 60 is a proper subset of the set of highly arithmetically decomposable. So in this way, we could relate quite a few interesting concepts what Ramanujan found during that period. And I think it's a nice time to stop. Thank you very much.
Thank you. Such an interesting talk. It's hard to believe this isn't your main area of research. But then you're working with the gurus at the top of the mountain.
And it turns out that number theory was my high school crush. I do believe it sometimes but now.
Thank you. That was very entertaining, and it fits into this theme that we have going forward, bringing together different fields and trying to create links between different areas of research. Now, I think we can open this for questions or comments. We have a little time. And Can I check with the experts? Is there a way for us to check if someone online has asked questions? So please bring it to our attention. I saw some hands up.
Is there any connection between this partition and the partition function in physics and statistical mechanics?
You can put I mean, yeah, in statistical mechanics, of course, partition function has a different meaning. But yes, you can, this partition has a very important connection with quantum mechanics calculations, actually. So they are all interrelated in a very.
I saw another hand. Yes,
It's very fascinating, these numbers. Just go back to Ramanujan's formula with Hardy.
Oh, okay.
I think what is fascinating about it's unbelievable how he came up with those.
Oh, yeah. It's very hard to say. He always said he dreamt them, but yeah. Yeah.
That's a big fascination, especially when you see you got in the summation you got GDN, the derivative.
Yeah.
With respect to n, which is n is it's a discrete natural number. So how do you do the derivative?
You first consider it to be non-discrete, do the derivative and put it back in.
Yeah.
Ramanujan used to do this trick every time.
Yes. But I think you may understand, being a relativist, you may understand where I'm going with this thing, because with the Gauss-Bonnet theorem in relativity, being scaled down now to 4 dimensions, because it works in dimensions higher than 4, which some people don't find palatable. But to bring it down to 4 dimensions, you end up doing the same kind of thing. And that's a big controversy in that game.
No, you can actually, but if you have the proper mathematical thing, like 1 plus 2 plus 3 plus 4 till infinity is minus 1 by 12, according to Ramanujan's sum. But again, Ramanujan's sum is not our usual sum. So one has to actually differentiate between these two very clearly.
Yeah, that's the Japanese Tomozawa actually has a paper on that, called dimensional regularization, where he does this, and that's how it makes that game a game you can play. I mean, it works in certain cases. It's quite interesting.
The same score. There's a whole section called analytic number theory. In other words, number theory, which is studied as as something which has got a lot of discrete variables, continuous variables. And a lot of results in number theory arise from that
dimension.
There's no questions online.
It's again, it's true that highly decomposable numbers satisfy this NS prime. So you have implication in one direction now.
Yeah.
Do you try other direction? If you have a number, say NS prime,
it doesn't work.
NS.
No, it doesn't work.
Yeah,
you have the floor.
Yeah, the comment I want to make is this rather sneaky way of regarding a 2-element sequence as an arithmetic sequence. Now, when you talk about a common difference and you have a single difference, it's not common anymore because you can't compare it with anything else. Right? So the question as to is it allowed, are you allowed to count even those sequences which are, fake arithmetic sequences? But we can get by that with the formula that we have. All you have to do is to just pull out all and those sequences are very easy. It's just S minus 1. So you've got genuine formulas for even those which are genuine.
But like, as I said, being like Euler, if you say, okay, P of 0 is 1, give some marks, so yeah, we can keep them as well.
So, is anyone else online?
No questions online.
Yes.
Can we go to the slide where it says NS even it can only have bases of a perfect square?
Oh yeah. Oh, that's a very nice, cute proof. You can yourself do it immediately. Yeah.
In the table above it, So I'm trying to observe the even values, the ends.
Yeah. Which you see, it's only for perfect square. You see 20, 16, then 25, 30, 9, 14, so on. It's a very simple proof, by the way. Nice, cute proof, but it's, yeah.
Since I can put this way, it should be faster. Ritu, coming back to Ramanujan's approximation.
Yeah.
Approximation. Did you try to plot the scale error, say, subtract, approximate?
Oh, yeah, no, not me. That has been done during that
Because
time.
I would assume it is 11.
Yeah, beyond 100, the error goes down to, I think, 6% or 5%.
Because I mean, when you put it like that.
Yeah, I know.
Exactly
Yeah.
that, right?
So beyond 100, it goes down like 6% of it. It's very simple.
Because he was famous for
Yeah.
giving a very good approximation of number, which requires just few curves.
Is there any way to somehow use your table there to find the prime factors of, to factorize? Can you do that?
It is the other way, yeah, of course, but first we need factorizations to get this table. So,
Sure. And
Yeah.
factorization is known as a hard problem computing. And the question is, can you out of your
yeah, but then how will you generate the table? Because you see, to generate the table, as the algorithm goes, we need the factors.
I got it. I mean,
Yeah.
you have all these patterns found in there. Can you somehow use that to find it?
Yeah, it would be an interesting way to look at. I mean, we haven't thought about it.
I can ask one more question. In the last conjecture you made, how far did you compute the things before you made the conjecture?
Well, I used all the highly composite number what Ramanujan gave in 1915. After that, people,
What is the largest one?
oh, it went up to 10 to the power 7 or 10 to the
Oh, okay, quite a good.
yeah, quite a good deal.
And so it's
Yeah.
up to that point of view.
Yeah.
it's like-
Yeah, let me just put the class table down. The floor function of ms over s,
Yeah,
the very last column,
yeah.
that is always 2.
The floor is always 2.
The floor is always 2.
Yeah.
From a certain point on.
Well, yeah, from 60 onwards. You see, NS is stopped at somewhere 2.6.
Yeah.
So if you take the floor, it is 2x.
Yes, last question, and I think some people have to go up to other venues, so we'll have to stop at the point.
Have you ever looked at using these types of summations to other types of like special number theory problems, like for example, Goldbox conjecture, looking at every positive integer?
Very difficult to say. Very difficult to say. From here, we got a characterization of primes. That NP equals P. In a, but to how to put it in Goldbach conjecture, I have no idea.
I think with that, we'll have to bring it to an end. Let's thank Professor Goswami.